Okay, hi everyone. Thank you for coming to today's robotics seminar at UIUC. I'm today's student host, Wei-Chen Huang from the Intelligent Motion Lab, and I'm very glad to introduce our speaker, Professor Wanxin Jing, to you all. Wanxin Jing is an assistant professor in the School of Engineering of Matter Transport and Energy at Arizona State University. His research lies at the intersection of robotics, control, and machine learning, with a focus specifically on context-rich textures manipulation, physics-grounded robot learning, and human-centered autonomy. Before joining ASU in 2023, he was a postdoc researcher at Grasp Lab at the University of Pennsylvania with Professor Michael Posa. He received his PhD from Purdue, and his work has been appeared in leading robotics and machine learning conferences and journals, including TRO, IGRR, RSS, ICRA, and NIRIPS. He's currently a associate editor for IEEE Robotics and Automation Letters. And today he's going to talk about his lab's efforts in context-aware control and learning for vectors manipulation. So let's welcome his talk, and please go ahead, Wanxin.
Thank you, Rich, and thank you everyone for coming. And I'm super excited to be remote to talk about our recent progress. Thank you for the invitation. My talk will be focused on physics-grounded dexterous manipulation. Um, so let me maybe start by talking about some motivation, basic motivation about why the contact-rich dexterity is difficult. If you think about human hands, right? So our human hand can, amazingly do a lot of manipulations with different objects. We can frequently making breaking contact with object without even thinking about it. However, humans, this kind of dexterity takes multi-years to develop based on the biological studies. A fun fact is that if you look at our hands only account for 2% of the body areas if you measure it in the area, right? So, but it requires 20% of the motor context to control that. So therefore, even for humans, dexterity is not trivial at all. And from a robotics perspective, the complexity is mainly from contact physics. So the contact events are essentially sparse and highly non-smooth. So the outcome of contact-rich manipulation systems, depends critically and like sensitively on the lot of factors such as geometries, physics, timing, and the fraction. So even for this like a simple 2D pinball game, if you look at the optimization landscape, so you can see it's quite irregular, right? So a lot of spikes, a tiny change of the control input can dramatically change the outcome of the systems. So given such a dexterity and the challenge of the dexterity, so I believe that if we want to entirely solve the dexterities, we are not only need to think about the end-to-end learning, but also we need to also make use of some physics and do some explicit physics reasoning. So let me make the discussion more concrete by decomposing this contact-rich dexterities into a hierarchy of multi-layer reasoning and planning layers, reasoning and planning layers. So let's just think about one simple case where robots opening the door and get some food from the refrigerator. So there are a lot of reasoning going on. So at the very top, we have the semantic reasoning, right? The robots need to think about what task to achieve. And then that goes down to the geometric and the kinematic reasonings where robots need to think about the geometry of this real world and figure out what regions is more useful to touch, right? So and what angles, what poses to reach. Then with this geometry reasoning, then it goes down to a very critical layers, which is contact dynamics reasoning. Basically, robots at this layer need to real-time and continuously regulate, the contact forces by making and breaking contact frequently, and also, the deciding the different contact strategies such as rolling, sticking, separation, and even speeding, making use of the friction. And then all those information goes down to the lowest levels, motor tracking controllers to achieve the motor command at a high frequency. So I want to bring your attention to this context dynamics layers. My key point is that this layer, the context dynamics reasoning layer, is actually the key bottleneck of the the dexterity design. This is actually where the sim to real gap really comes from, because we are talking about the dynamics, the motion force relationship constraints, and we really didn't have a good models, a good understanding of the what the actual contact dynamics looks like and what is the actuation dynamics. A lot of uncertainties, and also this layer will also contribute to the data inefficiency, because you are talking about the contact, it is essentially an under-activated system. So the reward is sparse. You need to explore a lot of the contact interactions to get a positive, meaningful reward. Of course, this layer is also related to the force and the safety, the applications. But if you look at the existing, the progress in the dexterous manipulations, people would like to use end-to-end learning to, bypass this hierarchy, say even directly learn a policy from the observation to the motor controller. So I would argue that, the end-to-end learning are really good at upper level reasoning. They are really good at, the semantic reasoning, the geometric reasoning, but they are relatively weaker at this context dynamics reasoning. So this is the key hypothesis, and this is the key thesis of this talk. So my argument is that if we can, add a little bit of the physics structure, even though it's a very simple physics structures, we can potentially to address the weakness of the end-to-end learning, and we can close the gap between we have mentioned, for example, sim to real data efficiency and safety critical issues. So this is the key hypothesis underlying much of my talk today. So, so in this talk, I guess the central piece I would like to introduce you to is our recent progress towards building is physics structures. So where I would like to introduce you a very simple analytical and lightweight contact physics engines we have developed for 2 years. So we use this physics structure, contact physics structure, as a backbone to develop the different types of the contact-rich dexterity and manipulations. I would also emphasize that this contact physics structure is not only a simulation component. It's not a simulator component. But also like a reusable and a computational like a structure. We can integrate this contact physics structure into different types of manipulation design and dexterity design, autonomy design. So in particular, I will use these structures to talk about like 3 types of the design algorithm design. One is we can use this structure to do real-time like contact predictive control for solving some like really challenging dexterous manipulation, for example, in-hand manipulation. I will talk about how we use this contact physics structure to to develop the policy that can overcome the sim to real and achieve long horizon dexterity. I will also talk about how this structure can go into the perception part. How do we learn world modeling, physics aware modeling from the from the videos more efficiently. So let's just start with this contact physics structure we have developed in our past 2 years. Let me start by talking about some background of the contact mechanics used in the existing physics simulator. So most of the simulators are built upon the complementarity-based contact formulation. What does that mean? Okay, complementarity basically says it's just it's a mathematical equations to describe the force motion constraints for the contact pairs. There are 2 variables, 3 conditions. The one variable is the contact forces. The second is the distance between the 2 rigid bodies. And essentially, the complementarity says that when the 2 bodies are in separation, meaning that the distance is larger than 0, the contact forces has to be 0. And when the two bodies are in contact, distance equals 0, then the contact forces has to be larger than 0 to prevent them from penetrating to each other. So there's 3 conditions written as this compact form. So therefore, in the existing physics simulator, at each time step, the physics engine need to solve both the post-contact velocity and the contact forces by satisfying two equations. One is Newton's equations, right? It's Newton's law, F equals ma, and the second equation is the complementarity constraint for the contact pairs. So, but a little bit complex is that these complementarity constraints can not only model the force gap complementarity in the normal direction as we have shown in this figure, but also can formulate the Coulomb friction laws, which basically offers a constraints for the force motion in the sliding case and in the sticking case using the friction cone. However, solving this complementarity at each simulation step is quite heavy, right? As computationally heavy, because essentially the complementarity is a binary constraint, it's an NP-hard problem. And so this will significantly slow down the simulation. Then a seminal work, proposed by Anitescu 20 years ago said that, we didn't actually need to solve this complementarity, which is NP-hard. We actually can make it as a convex optimizations. How do we do that? The key secret is to reformulate only the frictional sliding case. How does the reformulation works? Well, so in the classic, the complementarity formulation, and it said that the sliding velocity between two bodies, the sliding velocity has to be in the tangential plane of the two bodies. But Anitescu said that instead of the constraining the velocity in the tangential plane, we can make the sliding velocity on the edge of the dual cone of the friction cone in this red angle, triangles. So of course, this can bring in some the physical artifacts. However, the computational benefit is huge. It turns out that after we have making this modification and the previous complementarity constraint on dynamics becomes the KKT optimality condition for a convex optimization problem. What does this mean? This means that at each time step, we didn't have to solve a complementarity problem. We actually just need to solve a convex optimization at each simulation step. This is a huge computational benefits if you want to develop really fast simulator. However, this is the background. This is the state of the art of our simulator. For example, Majoko used this kind of formulation. But I was trying to argue that if you look at this simulator, it still require to solve a optimization at each time step. And if you look at the size of the optimization, it's at least the computational complexity, at least the quadratic in the number of the potential contact pairs. Then this motivates the rethink about how we can have a very simple but very effective contact modeling. So we have proposed in our lab last year a new contact model called the closed form analytical contact mechanics. So there are lots of the derivation here. I will just not bother you guys with the derivation, but I will directly give the results. So first of all, the key idea of our new contact mechanics is build a key idea, a simple idea. We want to directly generate the contact forces between two bodies analytically from the dual cone penetration. So let me explain how it works. So this is the final velocity. This is the post-contact velocity we want to solve. The V plus equals two terms. If you look at the first velocity term, this is the smooth velocity under the non-contact forces. Basically, you can solve this V velocity analytically from F equals ma, right? Newton's law. And the second term is the correction velocity because of the contact forces. Okay, now let's see how to calculate this contact forces, lambda here. So let's assume that the object is only moves under the non-contact forces, for example, gravity. And then this object will penetrate the dual cone, which is this red triangle. And then we can analytically calculate the penetration depth. And then we can develop an impedance algorithm, the models on the edge of the dual cone, which basically a spring damper model to calculate to prevent the penetration of the dual cone. So this is exactly the intuition behind our the key ideas. We generated the contact forces analytically by establishing a impedance mechanism on the edge of the dual coin. So you can see the lambda here has two terms. One is the spring forces, K is the spring stiffness, and D is the damping forces. So this is the basic idea of our closed form mechanics. There is no the optimization and the complementarity solve. You just need to do one virtual prediction using the smooth velocity and calculate the forces and correct the velocity. That's it. And you may be wondering, okay, such a simple contact model, can it capture the different contact modes, right? In the simulation, in the contact modeling, one of the difficult part is how do we capture different frictional the contacts? So well, actually, it's very simple and it's very elegant. So in fact, the contact modes are automatically determined by the activation cases of the dual cone faces. If you look at this lambda here, there is a plus. Actually, this is a ReLU operation, basically. So the different activation of the ReLU components determines which faces of the dual cone is activated. So let's think about the following scenario. If none of these faces is penetrated, none of the dual cone faces are penetrated. Basically, there are two objects are in separation. That means that lambda equals 0. There is no contact at all. And if the object is penetrating on one side of the dual cone, that means the sliding, because in the sliding cases, the contact forces should be on the edge of the friction cone. And if the two faces are penetrating, and then it means the sticking, because the sticking, the contact forces should be inside of the cone. So we can mathematically prove that the Coulomb friction law can be automatically satisfied using this simple model. Okay, let's go back to the fundamental questions. Why we need to care about analytical closed form contact dynamics? Well, the main motivation is because of planning. Okay, if you want to use the model to do the planning and to do the learning stuff, so let's consider one case we are using the classic existing complementarity-based contact model. If you want to do the planning, of course, you need to write down the cost function subject to the contact dynamics, and you optimize the robot control input and also the dynamics and also the contact forces, right? This contact forces will implicitly encode the contact modes. But if you want to solve this problem, you look at here, look at this constraint. This constraint is a complementarity constraint. As I said before, this complementarity constraint is a binary constraint. So therefore, the whole problem becomes a mixed integer problems. It has a combinatorial complexity, which is the exponential to the number of contacts plus and times the planning horizon. So if you are trying to using this optimization to solve the contact rich manipulation, in-hand manipulation, we are basically looking at the complexity of 2 to 100. That's basically intractable, right? So at least the real time. So now let's look at why we need this complementarity free contact dynamics. If you have the complementarity free contact dynamics, what we need to do is just to put our explicit model in, and this explicit model can implicitly handle different contact modes. You then need to explicitly handle the different combinatorial constraints. And most importantly, you can use any off-the-shelf solver to solve the same problems at very high speed. So this is one of the benefits of using the analytical contact mechanics. So based on this contact of complementarity free model, we have developed the contact predictive control, very simple paradigms. So if you want to solve this in-hand manipulation, there are two steps. The first, at each control step, we just need to do the clean detection and generate the potential dual coins. And put the dual coin into our complementarity free contact model and solve them. And then generate a robot action apply. This is the model predictive control style, right? So this is how we can use the simulation, how we use the model predictive control, a contact predictive control with the complementarity free contact model to solve different types of the multi-contact manipulation. Again, what you are seeing is just in simulation, we run our MPC in Majoko simulator, And there is no learning at all, just online optimization, the NPC optimization around 100 Hertz, and most importantly, it has a very high successful rate. So I will just skip. Maybe they'll talk about more demos later on. So we also tested this community-free MPC on the hardware. This is examples. This is a task we call the dynamic on-trip reorientation. You can see we control the robot joint angles to move the trace to use the friction to slide the object to its home position. You can see the human just use the stick to like perturb the object, and the train just use the sliding to make it back. So again. No learning at all, just to use optimization to do that. The MPC 80%. I think the nice part of this demo is that it exactly shows the capabilities of our models to capture the friction, because the friction control is actually not trivial in the contact control. All right, so most recently, we have moved from a contact modeling to a GPU accelerated simulator on top of that. So we call our new simulator called the conference sim. Okay, so some background. So for when we talk about a classic simulator, at each time step there are 3 stages, right? At each simulation step. The first stage, clean detection, then contact resolution, basically solve the contact dynamics, and then time integration. And because we have the new contact models, we can just analytically solve these contact resolutions using our computationally free models, and without solving any optimization, right? So it's a huge computational save. And in addition to that, we have extended our models to be able to capture different types of frictions. Not only the tangential friction, we can capture the torsional friction and rolling friction. And most importantly, when we develop our simulator on the GPU, that we find that this contact resolution and can be solved in a decoupled way. Basically, the contact resolution is decoupled across the different contact pairs. This can directly map to the GPU parallel simulation, parallel computing, right? So each GPU kernels can only responsible for one contact pairs. This allows us to do the scaling and GPU implementation and GPU simulations. And this is different from the existing simulator where they need different kernels to collaboratively solve a joint optimization at each simulation step. So because of this, this new simulation, and we have done a very careful evaluations compared with other state-of-the-art GPU simulators. Specifically, we made it compared with the MJ Warp, which is a GPU re-implementation of the mature code on the NVIDIA GPU hardware. So the most significant benefits or advantage of our model is the scaling. So our method is at least 2 to 3 times higher, the throughout compared to the MJ Warp for simulating this contact dense the same. So if you look at these 2 figures, I just put it here. So the y-axis is FPS. This is the frame per second, the throughput. And you can see for different number of the contact pairs in the same, our simulators is faster than Majoco Warp. And if you're talking about the parallel simulation of multiple scenes, our simulator again is twice faster than the Majoco Warp. And I would argue that even this very simple contact mechanics, it also achieves a meaningful, comparable physical fidelity compared to MJ Warp. So you can see in this top left corner, this is one corner case. We are simulating different objects contacting to each other. The left is MJ Warp, the right is a conf-free. You can see a conf-free is 5 times faster, but simultaneously you can see the Majoco Warp has a lot of penetration, and the conf-free, at least for this corner case, is not that bad. And you may ask, okay, why we need to care about why we need to use these conf-free simulators? why didn't we use the Mujoko warp? Okay, so I would argue that the Comfrey simulator has the benefits of the speed, right? So if we have the very fast simulators, we can directly put it into the MPC, sampling-based MPC, to directly control the hardwares with high frequency. So this is the example. So we put the Comfrey same simulator, GPU accelerated, into the sampling-based MPC, MPPI, to solve this in-hand manipulation. And the performance is very fast. So our simulators can achieve 50 hertz on average for the different control scenario. Actually, it's 3 times faster or 3 times lower latency than we use the MG warp plus MPC. And this, the speed advantage can bring us like 20% of this increase in successful rate. So all these demos has just, this is just like a real demos for the using our simulator to directly do the control. And we also like run our conference same MPC on the hardware. Sorry, on the to solve like the bimanual manipulations in the mature code environment. So this is trying to test like a same to same gap because the MPC used in our model, but our MPC is running on the mature code. So we use the conference to solve the different types of the bimanual manipulations. So priority the object into different targets. It has a high performance. So it can somehow reflect a comparable like a sim-to-sim gap. And again, we are also moving to like using the Comfrey MPC to solve some other challenging tasks. For example, dynamic survey targeting for the humanoid robot. So we have 6 demos here. So for each demo, you can see, for example, the first demo's left side is the kinematic reference replay. Mapping from the human motions. And then on the right side, we are using the Comfrey MPC to optimize the motion, to track the motions, but to satisfy all the dynamic constraint and the contact constraints. So this is the dynamic retargeting. You can see, again, we apply the Comfrey same MPC in the mature code. It's behaved quite well. And so this is how we use this new physics simulators to solve the contact-rich manipulation. Yeah, maybe I can. Please ask any questions if. Yeah.
So I just wanted to understand when you're adding these springs, does that mean that it's possible that even when two things are not in contact, there is some residual force? And
no.
I see.
No, actually, because we have this plus as well. So we have this plus as well. So after you calculate the spring force, you need to compare with 0, which is also the penetration. Yeah. If there's no penetration, there is no spring force. Yeah.
And on the flip side, can you also, how do you compute the force such that there is no penetration? Is it possible that like Mujoko does have some penetration?
Yeah, right. Yeah.
In this case, do you end up having any penetration, or there's no penetration at all?
It has a penetration in order to generate the contact force, but the penetration into the dual coin. It's not a penetration. You can say this is dual coin. This is a rectangle is a dual coin.
Yeah.
And this line is the ground. So they are penetrating into the dual coin. So actually, they are very close. Yeah.
But the right-hand side figure seems to suggest that the object also ends up penetrating.
Into the ground. This is just for illustration.
Okay.
Yeah.
Got it. Thank you.
Yeah, no problem. So, okay, next, and then that comes to my next part. How do we use the physics structure? Wait, yeah. Okay. How do we use a physics structure and simulator to design better, the long horizon and short distance?
Actually, I add another quick question. Sorry.
Yeah. No problem.
So how does this compare with Isaac Sim or something like that?
We have not do that right now. So I guess we will have to that.
I see. It's more approximate. I think Isaac Sim is less accurate than Mujoko. I don't know.
Yeah. Isaac Sim is based on the classic complementarity model, but they are in order to do that parallel, and they are sacrifice the solution accuracy. So they're not completely solved to the stop of the complementarity. They just stop somewhere So there definitely there's some like inaccuracy in the fidelity loss because of the computation, like the solver and some. And in terms of the model, I think the model itself is I think it's comparable to the Majungo. Yeah.
I guess one other follow-up question. Sorry. So if I'm interested in doing policy learning in simulation, then I mean, so for doing MPC and MPPI based control, I can understand that you need very precise contact modeling. But if I'm trying to learn a policy in simulation, do you know how does accuracy of simulation trade off with accuracy of the learned behavior?
Well, that's a good point. That's a good point. We have not studied comprehensively about how the RL policy trainings, the accuracy of the simulator factors of RL sim to real get of RL policy training, but we do have some experience of how the accuracy of the policy, how accuracy of the simulator affected the MPPI, MPC on the hardware. So my philosophy, I will talk. Maybe I will talk about it later on.
Sure, thank you.
Yeah. I'll talk about it. I'll put it in the final takeaway. So let's jump to the second part, which is how we can use the physics knowledge to address this long horizon sim to real gap for the manipulation. Let's go back to the hierarchy, right? And we have talked about we can use the conference MPC to solve this to solve the really good at like a local context reasoning, right? Reason about local strategy, for example, breaking and sliding, rolling, sticking, all these of that I will call the local context strategy. And one of the missing pieces is that the MPC, because it's a local optimizer, right? It cannot give you the global geometry reasoning capabilities. For example, if you are manipulating a huge object, the MPC cannot tell you what is the most promising contact regions for the robot to touch. So this is the benefits. This is the drawback of the MPC. And then, how do we solve that? Well, we solve that. Okay, we need actually a higher level policy to guide the lower level MPC to this to address this, to overcome this locality issues of MPC. So therefore, we have developed decouple this dexterity policy design into two layers. We have the higher level just to tell the MPC, okay, what is the most promising regions to touch globally. Okay, we use a learning-based method to do so because if you think about humans, this is like an affordance, right? So if we look at humans, if you human manipulate an object, the human based on our experience, we can immediately tell which region is the most rewarding to touch. And using this global contact region selection, we can send it to our local MPC, and we can make use of our fast physics-based MPC to do the local reasoning. Basically, the low-level MPC just answers how to touch. The high level is just where to touch. So this is like a decoupled design for the dexterity. So right now we have just focused on this hierarchical policy design on the application of the non-prehensile manipulation, just pushing different objects of different shapes. So this is the whole pipeline, okay? So we have a reinforcement learning policy tells the MPC, okay, where to touch, and the MPC will just reason about local contact strategy. And but there is one design questions. What is exactly the interface? Okay, what is the interface between the learning-based policy and the contact dynamics policy? Okay, so in order to answer these questions, and we have proposed a concept of representation called contact intention. So this contact intention has two elements. So first element, it tells you the most promising contact locations on the surface of the object for the robot to touch. Okay, this is C here. And the second component of this contact intention is the post-contact subgoal of the object. So basically, the reason why we need to have this post-contact subgoal, because if you think about long horizon manipulations, maybe some different stages and different subgoals require different contact configuration. So they combined as the contact intention. But if you look at this contact intention representations, it is object-centric, right? They all care about the object pose, the shapes, And it's also like the robots embodied agnostic, right? They didn't need to have much information except the number of the n factor. They didn't need other information about robot embodiment. So it's object-centric. And because of this, and also because this contact intention is all about geometry and kinematics, and we expect it has a minimal sim to real gap. So I will demonstrate this in this following in our parallel experiments. Okay, with this contact intention, this is the overview of our hierarchical policy closed loop. So at each time step, at each the decision step, the reinforcement policy will predict the contact intention, the subgoal and the contact location. And this contact intention will parameterize, will dictate the cost function of the local MPC, called local contact reasoning MPC. And then local contact MPC just reasoning in the near next to the contact location and moving the object to the subgoal. So this and close the loop. Of course, RL policy is running slowly, and the MPC can run very fast. So this is the whole idea. So I want to also like a little bit details about like this higher level RL policy, because we have tried different policy architecture, and we find this is the best. Okay, so this is the RL policy at a high level, predicting the contact intention, and we find that the observation space is critical in order to make the policy generalizable and work. So we have three components for the observation space. One is, of course, the geometry, the point cloud of the object. Also, we have the target information, right? And most importantly, we also need some clearing components. So the clearing components is the closed distance between each point on the surface object to the nearest environment surface. So the reason why we incorporate this observation is that we will give a policy a sense of like environment clearing in order to better generate the contact intention. So this is the policy design. And when we train the RL policy, of course, we need to incorporate the lower level MPC to train that. But the good thing is that because this contact intention is robot embodiment agnostic, so we can just we don't have to like put the entire robot in. We just abstract the robot using the end factor point to train policy. And this is the training learning. This is learning curve for the RL policy. Of course, we are trying to make the policy to be generalizable to different shapes when we do the pushing, the object of different letter shapes. And the left is the training successful rate is very nice looking. But I want to emphasize the right side. So we have compared our hierarchical policy with end-to-end policy, RL policy. So the same observations, but end-to-end policy just directly generates the robot joint actions. So you can see the difference. You can see, how much data we can save by using this hierarchical decomposed policy architecture. And of course, the most important thing is sim to real. We train the RL policy in the simulation using a very abstract robots, and that's it. And we directly, port this RL policy with hardware MPC and to do the long horizon pushing. You can see this long horizon pushing. You need to the high level policy need to tell the lower level policy which faces of the object need to push to switch. The same policy for different objects. The same higher level policy for different objects, and a highly successful rate. So this is the second part of the work. So I want to use just like one slide to talk about the benefits of doing so. So as I have said at the beginning, so the main bottleneck of the dexterity comes from this contact dynamics reasoning layer. And what we have done is we still use the end-to-end learning to help us to generalize to different shapes and to do the long horizon planning, find a global solution. But we also offload the complexity of this layer, the contact dynamics layer, to the physics-based method. So therefore, we are building like this policy in a bi-directional way. We are the learning is responsible for the higher level reasoning, but we use the physics to build from the bottom up. They both meet in a representation interface called the context intension. And let me see. So next I will jump to the third part. All right, third part is about perception and the video to physics learning or world modeling. Okay, we talk a lot about the physics simulator, right? So where we get the physics simulator, how we identify the simulator in the first place. So, well, we can directly learn simulator from the videos. We have a lot of videos on the internet about the context-rich, the same. So in order to learn these physics simulators from the environment, from the videos, we need to just learn two critical kind of elements. One is the geometry of the environment of the object or robots. The second is the physical parameters, for example, mass, inertia, friction, and others, friction coefficients, for example. So when we learn the simulator from the videos, we have two supervision signals, right? So of course we have the vision signals. Vision contains a lot of information about the appearance, about the geometry. Vision supervision is dense, but simultaneously it's very noisy, it's occluded. But simultaneously, because we also have this physics prior, the physics structure priors, and we can enforce the learning with the motion consistent loss, right? So we can use motion supervision to enforce the physics accuracy. Of course, it makes the simulator subject to the physics law, but the motion supervision is very sparse because the contact is sparse, the meaningful contact is sparse. So I guess the design for this whole problems becomes how could we make use of the best of these two supervision signals to learn to more efficiently and accurately learn the simulation. So we have two solutions. Okay, the first solution is twin track, and we have proposed recently. So the idea is very simple. So we have the videos, right? So we use like existing amazing work trackers, foundational posts to do the tracking, do the reconstruction, basically do the SLAM for the object and camera pose. And then we extract some like geometry which can be useful in the simulator and directly simulate that, right? So of course we have not aligned the physics simulator. We have not learn the physics parameters. So yeah, you can see the simulation is bad. And so therefore, we just need to learn the physics simulator, identify physics simulators using the tracking informations by minimizing the motion consistent loss. And this is what happens at the later end. So it seems like it's better, right? But if you look at the simulation carefully, you will see the object is ghost floating, right? So it's not contacting, but it's like has the contact forces. And the reason is why we have this kind of the issues. Because we directly trust the geometry from the visions. Vision geometry is not that accurate enough for us to have this high accuracy simulation. So therefore, in the twin track, we have proposed a geometry residual concept to correct this. So the idea here is that we get this visual geometry, visual SDF from the visual pipelines reconstruction. But we also need to have some residuals to fine-tune this geometry to eventually make it becomes the clear accuracy geometry. And so how do we find out this geometry? How do we find the geometry residual? Well, we learn the residuals and we learn both physical parameters together by using the motion consistent loss. Okay, so this is one example, one demonstration of the previous videos. This is what happens after we have fine-tuned this geometry as well, together with physics parameter. We have done some other tasks, so this is the entire, this all the plots are, the learning process. We learn both the geometry residual plus the physics together from the video supervision and from the tracking by enforcing the motion consistency loss. If you can see, look at all this, learning process, the iteration, x-axis is the learning iteration. You can see actually geometry residual actually is very consistency. And, it's very it always gets the consistency convergence about the geometry. This is exactly showing geometry have to be fine-tuned in order to have like a very very kind of high fidelity simulation. But if you look at the other parameters, right? So same type of other parameters are not converging. I guess this is because of the the identifiability of the parameter, because multiple parameters, again, I guess multiple parameter can explain the same motion. But this is what this looks like. And so yeah.
So if you go back to the previous slide, I was just curious, is this a visualization artifact? If you look at the bottom right video, are they supposed to be completely overlapping, the rendered view and the real view?
Yeah.
But then
yeah, I think this is a visualization aspect, because the hand I thought is also like a mismatched.
Oh, I see. So there is a mismatch.
Yeah.
It's not that it's artificially just shrinking all the objects.
Yeah. So we have, I guess this is illustration or something. I didn't know. So it's very hard to like make a good.
Yeah. Okay. Thank you.
Hi, may I have a quick follow-up question?
Yeah.
So you mentioned about the unidentifiability of multiple physics parameters. Do you need any regularizations to make the optimization process more robust?
Yeah, I believe so. We have just added L2 norm regularization for the other parameters, not for this parameter, the residual parameter. I guess so. Yeah. Otherwise, I guess it will diverge. You can see the variance, right? You can already see the the kind of instability of the larger variance of the learning process. Yeah.
Yeah, I see. Okay, thank you.
Yeah. I guess one of the simple application of this simple track is just we have identified a simulator. I can use the training policy, but also we can use the robust tracking. Right? So in that paper, we talk about the robust tracking. We learn a simulator, and then we can just combine the simulator prediction versus and the visual tracking to do like a robust tracking. Because sometimes when we have the occurrence, we have motion blur, and the visual tracker is breaking down, right? So then we can rely on more on the simulation prediction to compensate for that loss. Again, this seems like the visual tracker is really bad because we have used a very simple visual tracker. It's not a foundational pose. We are using the feature-based tracker, so it's very simple tracker. So it's very fragile. I guess the foundational pose is more robust again to this. To the motion blur. And let's see. So I guess I have 5 minutes. I'll just finish all this last part. So recently we have a collaboration work about another solution to learn the videos. Learn the physics simulators from the videos. In an end-to-end fashion, right? So the problem formulation is very simple, right? So we are trying to find out what is the geometry of the simulator and what is the filter parameter theta of the simulator, such that we can simulate it and then render it, and such that we can minimize the loss between the rendered image from the simulator and also the real world image. The ground truth image. So I guess the very critical design in this end-to-end pipeline is how do we use the representations? How do we find the representations inside the simulator G here? So we have developed a unified representations, which of course use the Gaussian primitive, right? So Gaussian is very popular. But we use the isotropic Gaussian primitives. Okay, each Gaussian primitive has two components, two components. One is like a components for the appearance, and one is a components for the geometry. Because it's isotropic, so we remove the covariance and just use the scaling to control the size of the sphere. And with this, this unified representations, and then we just go back to our simulator. We change the the clean detection, because previously clean detection in the simulator are all using the mesh and SDF, and we can directly do the clean detection using Gaussian primitives. So it's very simple, right? So you give a query point, we just to find out the closest Gaussian sphere. And but of course we want to make it smoother because we want in order to do the end-to-end learning. So we softmax it, and then another engineering trick is trying to like carefully handling the surface, right? So because Gaussian has a volume, Gaussian primitive has a sphere and has a radius, so we need to have like some tricks to make the boundaries really clear. And with this, the Gaussian representations, the unified Gaussian representations, I think it's very clear to, divide the pipeline. So we have the Gaussian has the geometry components. So we use the geometry to do the clean detection based on the previous slides, and then we use the conflict to move forward, and then we predict the next state, right? Then remember we also have this appearance Gaussian components, right? So we combine them to do the rendering to predict the render the image. So you have the rendered image, then you have ground truth image, and then just do the photometric loss, and then backpropagate everything. Because everything is differentiable, the simulator is explicit, and the Gaussian clean detection is smooth, and of course we're using the Gaussian rendering is also the differentiable, so we can backpropagate everything here. So this is one very preliminary result because this is still a submission. So I just pick one task to demonstrate. So this is we are testing this long horizon prediction capability of learned model. So the left is the real world and the videos. The cube falling, the cube flicking, the lip hand is just like flicking the objects. And the middle is we learn this just using the video frames from left side. We learn simulator, and then the middle here. This is just a long horizon prediction. We only align the first frame between this simulator and also real world, and then we use the simulator to predict the future. And you can see it's aligned relatively well. So the last column is just like a no optimizations. It directly imports the Gaussian primitive to the simulator. All right, I think that's all of the. I hope I have not take too much time. So this is all the take the talk the covered I have covered. So I want to mention two takeaways from the lab from the experience we have done in simulation, the control, and we use. And first of all, I firmly believe that as long as we can import some physical structures, no matter how small, how simple it is, so we can significantly solve and bridge some gaps in the existing end-to-end learning. The second, I guess, is something more useful. I guess can go back to the questions gentlemen asked me. So for the closed loop control, a feedback-based control, running the simulator on the hardware, do we really need an accurate physics simulator? Well, we have compared. I think it's more rewarding to use faster simulator than the slow accurate simulator to do the feedback control. So this is the philosophy of we develop our simulator. We are not, of course, our simulator is not perfect to capture this very complex simulator, but our simulator is fast. When you have the faster simulator, you can do really high frequency the replanning. So this can somehow close the loop of sim to real. I guess it works really well in all the tasks we have tested. So that's all the stories of my talk. Of course, I finally want to thank all the people, some of the students and some of the collaborators. Without them, this cannot be possible. Thank you very much, and I would like to take any questions.
Yeah, thank you for the talk. Very wonderful talk, and I think audience can feel free to unmute yourself and then ask the questions. And I think there's a guy who raised his hand, Venkata. You can just unmute yourself. Yeah.
Got it. Yeah. Hello, Professor Wanxin. And yeah, thank you for the talk. I had, please correct me if I misunderstood. So you basically use this cone shape to, instead of having a binary logic, to have a range of forces where within which like your contact force lies, right?
All right.
So, and you also mentioned that you use visual data to estimate the objects, information about the object, right?
Right.
So, how exactly do you take into account, how exactly do you estimate the object's friction and compressibility from visual data, even before the robot grasps the object?
Oh no, of course, this is identifiability problems, right? So if you never grasp object, you never can optimize the friction, right? So so what we are doing is when we do the learning, we definitely just use a segment of the data where we have the rich context. It potentially help us to identify all the parameters, especially friction. Also, I forgot to mention one thing. So when we optimize the physics parameters, we also need to optimize the K and D, which is the stiffness and damping inside our simulator. These parameters can only identified when there is a contact, or your data contains contacts.
Got it. So you're constantly like changing and like fixing these variables, including including the cone as you're grasping the object.
Yeah. Yes. Yeah.
Got it. Yeah. Thank you. I had one more question. Where exactly can I find like a link or like a GitHub repo for Comfrey?
Oh, that's good. That's a good point. I will give you I'll send this link to the website. We are clean our codes, so definitely everything. So we have just put this. We have just put I send it in the chat box. So we have just put everything. Not put up a website, and we submit our archive variants to the archive. So you can look for. I guess it's released yesterday, and we are releasing everything here. And for the Comfrey simulator, and for people to try.
Got it. Yeah. Thank you.
Yeah.
Can I give some question?
Yeah, sure.
Yeah. Thank you for your talk. I'm just curious about the complementarity free, the dynamics. Is it the differentiable or because I heard that you're using the MPC, so I'm wondering you using the gradient based or sample based.
Yeah, that's a good point. I have just to talk about two types of the MPC. One is a gradient based, one is a sampling based. So when I first talk about this demo here, this is a publication in last RSS. So these are gradient based. These are gradient based MPC using the using Comfrey model. And when I talk about this one, this is also gradient based. This demo is also gradient based.
Wanxin, I think you are not sharing your your screen right now, so they cannot see which.
Sorry. I don't know why it's okay. Let me share it. Okay, yeah. Sorry, let me just repeat. So this demo, the demos we have published in the RSS last year. So this is gradient based. This is gradient based, very good and very stable. The performance, the 100 Hertz MPC, we actually use the iPopt. We use the Casati to do the optimization. And this demo is also optimization based, gradient based MPC. And when I talk about this demo, all the demos below, all the demos afterwards is sampling based because we want to test the high throughput of our simulator for the sampling based MPC.
All right, thank you.
Yeah. Oh, and maybe I can add like one more comment. I think when we took the gradient based, okay. When we talk about the gradient based method, okay. So there is a trick I need to mention that, as I mentioned, physics simulator including 3 parts, right? So 3 stages: cleaning detection, contact dynamics resolution, and the time frame. And what we have addressed for the conference is the contact resolution, but the cleaning detection is not differentiable. Okay, cleaning detection is typically not differentiable because you have a lot of the edges, right? So therefore, how do we use the gradient-based method to solve the MPC? Well, our trick is we are not update the clearing inside the MPC. When we go into the MPC, we just do the cleaning detection once, and then we freeze the cleaning detection results inside the MPC. So therefore, the MPC is just consider we have the fixed dew coin, and just consider how do we make the best use of the dew coin, of the fixed dew coin to do the decision. So therefore, if you go to the second part of my slide, second part of my talk, this is exactly this picture. So the MPC, because if you want to use the optimization-based, a gradient-based MPC, the cleaning detection is the main bottleneck which prevent us from do the global geometry reasoning. So therefore, we just freeze that, and we just tell the MPC, okay, I give you the clearing pairs. Tell me how you make the best decisions. You can either using a sliding, you can either do the sliding motion, you can do the spinning, you can do the sticking, separation. Yeah, I'm not sure if that makes sense.
Well, thank you for all the answering the questions. Does the audience have any other questions? If not, I think we can wrap up this talk. And thank you again for coming to this talk and sharing your amazing works.
Thank you everyone for the listening. Bye-bye.